just say something. Test, test, 1, 2, 3, 4. Great. I think, yeah. Okay.
Bueno, pues finalmente estamos listos para iniciar el taller de imputación de la no respuesta, algunas concepciones comunes equivocadas. Este es el título de la presentación que hará el profesor Jörg Dreschsler. Solo voy a permitirme leer algo muy breve sobre el profesor. Él es investigador distinguido del Departamento de Métodos Estadísticos del Instituto de Investigaciones del Empleo en Nürnberg, Alemania. En 2009 recibió su doctorado en Ciencias Sociales por la Universidad de Bamberg y en 2015 su habilitación en Estadística por la Universidad Ludwig Maximilians en Múnich. También es asistente de profesor adjunto en el programa de Metodología y Encuesta de la Universidad de Maryland, Estados Unidos. Sus principales intereses de investigación son la confidencialidad de los datos y no respuesta en encuestas. Es miembro electo del Instituto Internacional de Estadística, ISI, y es director asociado del Journal of Official Statistics y del Journal of Survey Statistics and Methodology. Con ustedes, Jörg.
Okay, thank you, Ricardo. It's my great pleasure to be here. I realized I'm the only one with 1.5 hour slots compared to the others with only 1 hour. So I'm not sure if this is a good sign or not, but in any case, the problem will be, I mean, if you think my talk is boring, I have to say sorry. You have to stick with me for another talk tomorrow morning, actually. But I'll do my best not to bore you. Unfortunately, I don't have any pictures for my grandchildren because I don't have any grandchildren yet. I only have a daughter, but I don't even have a picture of my daughter. But of course, she's at least as cute as Tom's grandchildren, as you might guess. But I'll try to talk today about some common misconceptions about imputation in general, and tomorrow my talk will focus on multiple imputation specifically. And let me see. Okay. So the content for today will be, after a little bit of an introduction and an introductory example, I'll talk about the common missing data mechanisms that are commonly used when talking about non-response, and then specifically focus on some misconceptions that I face pretty often when I talk to people about what the goals of imputation should be and what not. I think there's some common misunderstandings what the goals of imputation actually should be. So I'll talk a little bit about that, and then also why you should better avoid simple imputation methods like these mean imputation and stuff that is still commonly used in many agencies, as Tan said this morning. So very briefly, the two types of non-response, we heard that already. A unit non-response is when the whole unit completely refuses. It's not working? Okay. I should use that instead? Okay, if that is better. Then I'll turn off this one, I guess. Just keep it. Okay, so unit non-response is when the unit just doesn't participate in the survey at all. So we don't have any information on the survey variables, and the typical approach to deal with that is using weighting strategies, and I'll not talk about this anymore in this workshop today, but I'll talk about item non-response. So the situation where the unit generally participates but doesn't provide an answer for all the questions. And so we still have information observed for some variables, but there is some information is missing, and this is where imputation is typically used. And obviously, both types of non-response are most problematic if the respondents are systematically different from the non-respondents. And for illustration, I start with a very simple example for item non-response. So let's assume we would be interested in estimating the average income in Burundi. And you might wonder why we'd be interested in estimating the average income in Burundi. The reason is pretty simple. It's because I work at the Institute of Employment Research, as I said, and we have a lot of economists there. And so when I made up that example, I didn't want to use an example where they would say, but that's not a realistic distribution for the income in Germany or something like that. So I deliberately picked an example where I was sure that I couldn't be criticized for the distribution that I picked when I simulated the income distribution. Okay, so I picked Burundi, and I can tell you the average of that distribution still matches the average monthly income in Burundi, but apart from that, everything is made up. So in that example, I assume that my full population would consist of 1 million records, and the true relationship or the true model for my income is that log income follows this distribution, so it depends on education. And for simplicity, education is only a binary variable where 1 means that the person finished high school and 0 is didn't finish high school. And the probability that high school is finished is 25%. And now we want to estimate that average income in Burundi, so we conduct a survey. Okay, that asks just that one question: what's your monthly income? And now we run a small simulation under 3 scenarios, where in the first case everybody responds. In the second case, the probability to respond is 0.7, but it's constant across the units. And then in the third situation, the probability to respond also depends on the education. So people that didn't finish high school have a response probability of 80%. Those that finished high school have a response probability of only 40%. Okay? This is what the income distribution looks like in the population. So we have a clear difference, if I find out how that pointer works here, the clear difference between the high income, the people with high school degree and those with no high school degree. The average income is about 250 euros. And the average income for individuals with high school without high school degree is only 168 euros. And now I have this small simulation design where I repeatedly draw a sample of 1,000 records. So this would be our hypothetical survey that we are conducting. And I generate missing data according to the different missing data mechanisms that I described previously. So ones where the missing rate is constant, and the second scenario where it depends on the education level. And then we are interested in estimating 2 quantities. So what we're interested in is estimating the average income or estimating the average income for individuals without high school degree. Okay? And we run that whole thing 1,000 times. So we just a simulation as if this interview or that survey would be repeated 1,000 times. Okay? And here are the results. For the average income, of course, if there is no non-response, my estimate for the average income, so remember the true average income is this thing here, 252.64, and my estimate would be 252.45. So if there's no non-response and we had a simple random sample here, of course we would get unbiased results, and our coverage rate for our 95% confidence interval would actually be 95, close to 95%. And if the missingness does not depend on education, we still get unbiased results. The only thing that changes is that the variance of my point estimates, or the variance of this estimated average income, increases, which is not surprising because my sample size, the number of observed records will go down. So the variance will increase, but otherwise everything is still unbiased. But of course, in the last situation where missingness depends on education, we would underestimate the average income, right? Just because the response rate is higher for the lower educated. The lower educated have lower income, so they are overrepresented in the sample. I underestimate my average income, okay? And so my coverage rate would actually be close to 0. But now what happens if we're interested in estimating the income for those without high school degree only? Now in this case, we see that independent of the missingness mechanism, we still get unbiased estimates for all of our point estimates, and coverage rates are also okay. So again, of course, variances will increase in those two situations compared to if we have all cases, which is obvious, we have less data, but at least we would get unbiased results, okay? So the findings from that small example, just to get started, is that obviously item non-response will always have an impact, and variances will generally increase for our estimates, but inferences are not necessarily biased. And the bias depends on the response mechanism, but it also depends on the analysis of interest. And so this is the first, I would say, the first misconception that I often hear is that you will get, so it only depends on the response mechanism whether you get biased or unbiased results using complete case analysis. That's not necessarily true. It really depends also on the type of analysis you're interested in. So you could still get unbiased results in other situations. So you always have to consider both the way the response mechanism looks like and what you're actually interested in. Both have influences on the results you get, okay? And to be a little more specific about the different missing data mechanisms, we generally have these three missing data mechanisms that you probably heard about already. So we have either missing completely at random, missing at random, or missing not at random. And those three definitions have been given in a paper by Don Rubin in 1976, which is now a highly cited paper, but I always like the story that Don tells when he wrote that paper and he first submitted that, it got rejected and rejected and rejected. So he had to resubmit it to all sorts of journals until it finally got rejected. And he said it was probably the 7th journal or something that he submitted that paper to. And now it's one of the most influential papers when you think about non-response. So that is always, I find that always motivating. If one of my papers get rejected, I think of that story again and think, well, maybe my paper is just too innovative and I need to try another journal, okay? So the three response mechanisms. Some general definitions before we can look at that. So my Y here is basically my data set. So it consists of n records, k variables, and so Yij is the value for variable j for subject I. And then we have Y-obs, which is the observed part of Y, and Y-miss is the missing part of Y. And then we also have M, which is my missing data indicator, which is basically defined similar to my Y, but it's just a 0, 1 variable. So whenever Y is observed, it's 0. Whenever Y is missing, it's 1. Okay? And then we have a model for that missing data indicator that might depend on the data and on some parameters psi here, which are unknown. And if I have the missing completely at random situation, the missingness does not depend on Y at all. So I can simplify that distribution. Screens. Can you still see the other screens here? Okay, can I still continue? Okay, I'll try. So the missingness does not depend on the data at all, right? Which doesn't necessarily mean that the missing pattern itself is really random, but the important thing is it just does not depend on the data value. So it could depend on other variables. If those are uncorrelated with the variables that you have in your data, that doesn't matter. You still have missing completely at random. But in general, this is quite a restrictive assumption because in many cases you can imagine that missingness depends somehow on the characteristics of the individuals, and then you have these characteristics in your survey, and so It's quite a strong assumption. But it's also the implicit assumption in most statistical packages, because they usually do complete case analysis, so they only use the data that is fully observed, and you only get valid inferences in most cases, at least for this strategy, if you assume missing completely at random. Okay? But it's an unrealistic assumption, at least I think it's an unrealistic assumption in most cases, because you can imagine that response probabilities will depend on individual characteristics. There's only one exception where this might be realistic, is if you have missingness by design. So that could be if you ask some questions only for a subset of your respondents in your survey. So for example, if you take, there are these surveys that also take medical examinations, which are highly costly, and those are only performed for a subset of those individuals that participate in the survey. And then you have control over who gets selected for this medical examinations, and then you can ensure that this subset is really a random subset of the other individuals, and the selection does not depend on the other variables that you collected in your data. And in this case, this missing completely at random assumption might be realistic. But in other cases, I think you have to acknowledge that the missingness might depend on your data. And one situation, there would be missingness, a missing at random, where the missingness now depends on the data, but only on the observed part of the data. So it cannot depend on the part that is actually missing. It only depends on the observed part. And this is the standard assumption that you typically make if you do imputation. So you basically assume that your observed variables can predict the probability for your records to be missing. And it seems reasonable that this assumption is more realistic the more variables you have available, right? So if you think you can condition on a lot of variables, you can condition on age, on education, on race, and all these variables, the more you have, the more realistic it might be that these variables will explain the probability for your dependent variable you're currently looking at to be missing, right? And so that's one of the reasons why generally in imputation you often recommend to condition on a lot of variables in your imputation model, but I'll come back to that later. And then we have that final case where the missingness depends on all of y. So it also depends on the missing parts of y. And this is the missing not at random situation. And that's the most difficult one, because for that situation, you also need to model the relationship between the missingness and the unobserved part of y. And the major problem is because y is missing, you cannot assess these models from your data. You don't have that information in your data. So if you set up a model for y and m together, so a model for the joint distribution of y and m, you have to make some assumptions that you never can test with your data. And so either you have external information available that you can use for that, but in most cases you don't. And so one criticism of these models is that they are often considered to be subjective, just because you need to specify a model where you have no idea based on the data whether this model is realistic or not. And so in most cases, if you're in that situation, it's mostly recommended that you do some kind of sensitivity analysis where you make different assumptions about what the relationship between y and m is, and then evaluate how the impacts would be on your results you're interested in, depending on your assumptions about the missingness mechanism. But this is tricky because defining these models is not straightforward, just because you don't have any information from your data for the sensitivity analysis. So a quick summary for that. In general, you can say that the missing data mechanisms generally differ in the way the response probability depends on the data. So it either depends not at all, it only depends on the observed part, or it depends on all of the data, including the missing parts. And an important thing that we don't have the time to go into detail is that there's a specific situation where you can call the non-response ignorable, and that is always true if the missing data mechanism is either missing completely at random or missing at random, and the parameters that for the data, so my theta, are distinct from the parameters that govern the response process. So these two parameters, basically the parameters from the response process cannot put any bounds on the parameter space of theta, basically. They need to be independent in some sense. And in this case, the non-response is called ignorable for the simple reason that you don't need to worry about that non-response model. You don't need to specify a model for the non-response. You only need to focus on your data in that situation. And you only need to specify this specific distribution. So the distribution of your parameters you're interested in given your observed data. And you don't need to set up a model for the non-response, because the problem is whenever you try to set up these models, you often run into identifiability issues, and things can get really complicated once you need to specify a non-response model, and you don't need to do that in that specific situation. But that doesn't mean that specifying that distribution is easy. It's still tricky if you have a complicated non-response pattern. Getting inferences for that distribution often requires Markov chain Monte Carlo methods or other complicated methods. And you can basically think of imputations as being a tool to approximate the distribution. And that is basically the goal of imputation. You don't want to really get information on the missing values, but you want to approximate this distribution under specific assumptions about your non-response. And of course, the most important thing is to keep in mind that we can never learn from the observed data whether our missingness mechanism is missing not at random or not. It is an assumption that we have to make. We have to say, I believe that I have sufficient information in my data so that I can claim that the missingness can be explained by the observed part of the data, and I'm in the missing at random situation. I cannot test whether the data is missing not at random or not. Okay? So finally, the common misconceptions. Generally, imputation goals. Imputation only tries to replace the missing values with plausible values given the observed data, with the idea that once you impute the data, you have a nice rectangular data set again. And it's, of course, not the case that imputation is the only valid method to deal with missing data. So we have other methods, like you can do a fully Bayesian approach. You can use likelihood methods to directly estimate this distribution of theta given y-ops. You could do all sorts of things. The important thing about imputation is it just tries to facilitate the analysis of the data, because the idea is once you imputed the data, you can simply use your standard software again. So now, once the data is imputed, you can run your standard regression models. You can use standard statistical inferential methods to obtain inferences from your data, which you cannot, obviously, if there are holes in your data. So the basic motivation is really to free the analyst from the burden of dealing with deficiencies in the data so that he or she can focus on his or her analysis. So the idea is really then, once the data is imputed, you can really think hard about the actual analysis problem you're interested in and spend time on that, and not thinking about how to account for the missingness in your data. Okay? And some misconceptions that I'm often confronted with is, for example, it depends. At my agency, there are a lot of sociologists or economists, right? It's Institute for Employment Research. And obviously, this will be an argument that sociologists often bring forward. They say, you know, imputation, you're inventing data. You know, you're it's like magic, and you're mumbling over your cauldron, and then you make up this data, and it's all fake and invented, and that doesn't really make much sense, and I don't trust that. But it's important to keep in mind that imputation does not try to create any information in the sense that we try to recover those missing values. That's not the goal. We're not trying to get these missing values back again. And it's really only the goal to really try to use all the observed data. Because if you have all these different holes in your data and you do complete case analysis, you throw out all this observed information that you already have, and that would be a waste of information, basically. And so imputation only tries to make sure that you use all the information that is still there. It's not about filling in those missing values so that you recover the information that's in there. That's not the goal. Because, I mean, this information is gone. You don't know what the true value was there. And you should not try to recover that. You cannot recover that. And that's something that I find really important, because people, I feel, often miss that this is not the goal of imputation. So you only use the relationship that you find in the observed part of the data, so the relationships that are still there, to model the relationships for your entire data. And the only exception from that is if you impute under missing not at random assumptions, because then you actually need to make some untestable assumptions about this non-response process. But in other cases, you're not trying to recover that missing information, and that is important. And then when I talk to the economists at my institute, they say, you know, I don't like imputation because imputation makes more assumptions than when I just analyze the data the way they are. I just use the data that is left, and then I use standard complete case analysis and run my regression models there. Because they say, you know, it's all model-based, and I don't like models, and so they criticize imputation for that. And for that, I think it's again important to keep in mind that if you use these standard analysis methods, at least, and not apply some of those more sophisticated methods that really account for the missingness, then you generally only get valid results in most cases if you assume that your missingness is missing completely at random. So it's not related to the data at all. And if you do imputation, at least you get from missing completely at random to missing at random. So that's a step. I mean, your assumptions are less strong than the ones that you need to make if you do complete case analysis. And of course, the argument is true that imputations typically are model-based and all models are wrong, and so you might introduce some bias there. But especially when I'm talking to the economists, they usually fit models too. I mean, it's not that they are only in the design world. They really have their complicated models that they typically fit. And so the standard recommendation in this case then would be you simply include all those variables in the imputation model that are also included in the analysis model, just to make sure you reflect all those relationships. And that makes sense because if you consider, say, the economists interested in the relationship between education and income, right? The typical returns to schooling model. And you leave out education as a predictor when you impute your income. What would happen? You would basically, in your model, you assume that conditional on the other variables, there's no relationship between education and income, right? Because you don't include education as a predictor in your model. So you assume there's no relationship. And now, if the analyst later analyzes your data and is specifically interested in this relationship between income and education, the results will be biased towards 0, because for all the imputed values, you assume, basically based on your model, that there is no relationship, right? So you'll bias those coefficients towards 0. So the general recommendation, and this is really important, is to always include all variables in your imputation model that will be later used in the analysis model. Very important. And if you do that, you can argue that with imputation you basically make less assumptions than if you just analyze the model using standard tools and standard software. Okay? And then another thing, and that comes back to what I already talked about, is that people often think that imputation should really try to predict the missing values as accurately as possible. And if you think about that, it sounds reasonable. You know, you want to get back those values that are missing as close as possible, and that seems to be a good strategy. But again, imputation is not prediction, and that is something, again, which I think is very important to keep in mind when you talk about imputation, that there's a big difference between imputation and prediction. And what you often find, and that's even, you often find that even in published papers in scientific journals, is a measure to evaluate the quality of the imputation based on the hit rate. And this is often evaluated in simulation design. So where you know the true value, so you start with the fully observed data, you delete some cases, re-impute again, and then check how close your imputed values are to the observed values. So for categorical variables, for example, you would just check how often is my imputed value equal to the originally observed value, right? So this would be one measure. Or for continuous variables, you would look at the average deviation between the imputed values and the originally observed values. But the problem is that this is really not a good measure, because even if an imputation method scores good on that measure, you might still get biased results. And I have a small example just to illustrate that. So if we assume we want to estimate the unemployment rate, and I mean, all my examples are always economic examples, just from my background, but I mean, you can translate that in other contexts. So we are interested in estimating the unemployment rate, and the true unemployment rate would be 10%, okay? And we conduct a survey again 1,000 records. And we assume that our sampling mechanism was like this, that inferences based on the full survey would actually be unbiased. And we have a non-response rate that is 30%, and the missing data mechanism is missing completely at random. So in general, we are still in a pretty good situation, but we still want to impute, okay? And then we look at two imputation strategies. The first one imputes the missing values by drawing from a Bernoulli distribution with the probability of imputing that the person is unemployed with 10%, which would be the estimate that you would also get from the observed data. So we would use the observed data to estimate the unemployment rate and simply impute with the same unemployment rate for the missing cases. And the second approach is to say, I know that most of those people are employed anyway because I have a low unemployment rate, so I simply set all of them to be employed. Okay, so for the missing cases, I set all of them to be employed. And then the question is, which one of those two should be preferred? And now if we look at the hit rate, what would the hit rate mean in this case? We would always be correct with our imputation whenever the imputed value is equal to the true value, right? And so what we are interested in is the probabilities. So there would be two cases where we would be correct. The true value was 0 and I impute a 0. The true value was a 1 and I impute a 1, okay? So I basically need to calculate the probabilities for those two cases and simply sum them. And given that my imputation is independent from the original value, because I don't know the original value, the joint probability of those two is simply the product of the two probabilities. And now let's look at our hit rate for the Bernoulli imputation. So the probability in my original survey to have unemployed is 0.1. The probability of imputing that the person is unemployed is also 0.1. The probability that the person was employed in my survey was 0.9. The probability to impute that is also 0.9. So my hit rate would be 0.82. Okay, 82% of the cases I would impute the correct value. Now for deterministic imputation, I would say that the probability that I impute a 1, so unemployed, is 0, whereas the probability to impute employed is 1. So now I'm ending up with a probability of imputing the correct value with 90% of the times. Okay, so in this case, it's clear that the hit rate would favor the deterministic imputation, because I would be correct in more cases, right? In 90% of the cases, I would be correct with the deterministic imputation. But of course, what we're actually interested in are inferences based on the imputed data. And so let's look at what happens if we are interested in estimating the unemployment rate now. And so the unemployment rate is simply computed as counting all those units in my data, in my sample, where y is 0, so the person's unemployed, and divide that by n. Okay, it's just the rate of people that are unemployed, right? It's my estimator for the unemployment rate in the population. And of course, I can split that sum over all units in my sample as the sum over the observed cases plus the sum over the imputed cases. And what we need to look at if we're interested in evaluating whether our estimate is unbiased is to look at the expectation over the imputation and also over the sampling design, okay? And for simplicity here, I treat the response rate as fixed. So otherwise, we also need to take the expectation over that, but that wouldn't change anything regarding the results. Oh, and I lost my screen again. Maybe I shouldn't walk too much here. Maybe I'm hitting the cable or something. I don't know, but I always used to that. Sorry. Anyway, so it's difficult with the pointer now, but what you see is if we take the expectation, so the expectation here, and we don't need to go in too much detail, but the important thing is I don't really need to take the expectation over the imputed values when I'm looking at the expectation from sampling, because the imputed values are basically independent of the observed values. So in that sense, I'm only taking the expectation here over the observed cases regarding the sampling design. And the same then is true for the expectation from imputation, because those values that are observed, they don't change if I do my imputation. So here I only need to take the expectation over my second part of this summation here. And so what we end up with is, given that my response rate is fixed, I have the number of observed cases times the probability that y equals 0 for the observed cases, plus the number of imputed cases times the probability that I impute a 0 for the imputed cases. Okay, and given that we have missing completely at random, the probability, so the probability ops, PR ops, is of course still an unbiased estimator from the probability in the population. Okay. So now let's look at those two for our two different imputation methods. Now, if we use Bernoulli imputation, we know for the first part, of course, we have 700 units because the response rate is 70%. So 700 units are observed. And for those, the probability that y equals 0 is 0.1, because that's the true unemployment rate in the population. And then for the imputed cases, we have 300 imputed cases. And for those, since we use this Bernoulli imputation, again, we impute a 0 with a probability 0.1. Now, if we calculate that, we get back to 0.1, which is the true unemployment rate in the population. So now we have an unbiased estimate. But what happens if we do the same thing with deterministic imputation? So the only thing that changes here is that we use the probability to impute a 0 based on our deterministic imputation model now. And of course, that probability is 0, right? So that's the only part that changes here. So in the end, we would estimate the unemployment rate to be only 7% instead of 10%, right? So the whole message of this whole story is basically don't use this hit rate as an evaluation criteria. It's simply not useful because you can still get biased results for a method that might be preferable based on that hit rate. But imputation, the real goal of imputation is not to get back those missing values, but to allow you to get valid inferences for the population you're interested in. So you want to make sure that the estimates you get from your imputed data are still valid. And for that, you should not try to look at imputation methods that are good in prediction. Okay? So that's an important thing to keep in mind again. So coming back to the imputation goals. So the real goal is to obtain valid inferences from imputed data using any existing software that gives valid results, gives valid inferences with complete data. So we want to get approximately unbiased estimates for the population estimates. We want to get valid test results if we want to perform some hypothesis testing. So the retraction rate for our hypothesis test should be less or equal than the nominal level of the test. And then we also want to have valid confidence intervals for the estimates. So the actual coverage rate of our 95% confidence interval, for example, should be at least equal to the nominal coverage rate. Okay? And only if those goals would be fulfilled, then we could look at imputation methods that are more precise, that are more efficient, lead to more powerful tests, etc. But only once we fulfill this goal up here and not as a goal per se, right? So the only goal of imputation is really to represent the observed information in a way so that we can simply use standard statistical software and standard complete data analysis. And this sounds like a small goal, but it's I don't think it's a small goal because achieving that is hard enough. But it's important that this should be the goal, I think. And for the rest of the talk, I'll provide some examples why simple imputation methods should generally be avoided because they really fail on those goals. So in general, you can say that almost all imputation methods are somehow model-based methods. No matter if you use mean imputation or if you use ratio imputation or whatever you do, it is basically a model. You can always write that as a model. And so in the sense, almost all imputation methods are model-based, and then the question is only to find the best model in a way, okay? And you can write those imputation methods most generally if you say my imputed value for my y variable that has missing values is related to some explanatory variables. I mean, here I have a simple linear regression. It does not necessarily have to be a linear regression. It could be any type of regression model that you can imagine. But generally, you have some estimated coefficients here that you estimate based on the observed data. And then you have your fully observed predictors. And with those, you impute your missing cases. Okay, and then you might or might not have a residual term here, depending on whether you have stochastic or deterministic imputation. But in general, you can basically always relate almost all imputation methods to this kind of imputation structure. And then you can classify your imputations as, just as I said, either deterministic or stochastic, so whether you set that error term equal to 0 or not. you can say your imputation conditions on covariates, or it's a univariate imputation where you don't condition on any other variables. And then it could be explicit or implicit, where explicit means you have a clearly specified model, just like a linear regression model, for example, whereas implicit models would be more based on algorithms. So hard-DAC imputation would be an example for an implicit model where it's not clear how to write down that model specifically in terms of statistical terms. So what would be the error properties of that model? But you have more like a procedure that describes these are the steps to impute my values. And the major downside of these implicit models is then that it's a little difficult to obtain valid standard errors based on the imputed data, just because you don't really know what the properties of these imputation methods are then in the end. But to show again what kind of problems you run into if you use simple imputation methods, I have a simulation again, because I think it's always helpful if you have a few pictures and results to see what's actually going on. So it's a repeated sampling simulation again, where we try to evaluate the frequentist properties of different approaches to deal with missing values. And again, we look at those three missing data mechanisms. So we have missing completely at random, missing at random, and missing not at random. And I try to keep it very simple just to get the main message. So I generate a population which only consists of two variables, y1 and y2. Again, I have 1 million records. I generate y from a multivariate normal distribution. So it's a bivariate normal distribution. Both variables have a mean of 0, variance of 1, and a correlation of 0.5. And then I repeatedly sample from that population by simple random sampling. So we just have, again, a simple random sample of 1,000 records from that population. And we only have missings in y1. Okay? And then we have three different missing data mechanisms. The first one does not depend on y at all. So for all cases in y1, the probability that y1 is missing is 0.5. And for the other two cases, so missing at random, the probability depends on y2, right? So y2 is always fully observed. So I have a situation where I have missing at random, because the missingness only depends on the observed part of the data. And in my final situation, missingness depends on y1. So this would be a situation where I have missing not at random. Okay? And then I impute all my data sets with those different missing data patterns with different imputation methods. And then I analyze the imputed data using standard complete data estimates. So if I just use standard software to analyze the data. And I repeat the whole thing 5,000 times. Okay, and what we're interested in is, we're interested in mu1, so that's the mean of y1. We are interested in the regression coefficient of y1 in a regression of y2 on y1. So I regress y2 on y1 and look at the slope coefficient in that regression. And then I'm also interested in the other way. So if I regress y1 on y2 and look at the regression coefficient of y2. Okay, so these are the three estimates I'm interested in, and I want to see whether I get unbiased estimates. Okay, and we are interested in the bias of the point estimate and the ratio of the average estimated variance over the true variance. So we want to make sure that the estimated variance of the point estimate, so for example for the mean, so sigma squared over n, whether this is still an unbiased estimate for the variance of my point estimate. And then I'm looking at the confidence interval length just to see what is more efficient. And I look at the coverage rate of the 95% confidence interval, because I'm repeating that simulation. I can always check for each simulation run. Oh no. For each simulation run, I can check whether the true value from the population is actually included in my 95% confidence interval, right? I can do that for each one of those simulations. I just check, is it included or not? And since I run 5,000 simulations, it should be included in 95% of the cases. That's the definition of the confidence interval. And so I can check whether this coverage rate is correct. So whether my confidence interval covers the true value from the population in 95% of the cases, okay? And these are just the results based on the original data, so if there were no non-response. So the true values, of course, for mu1 would be 0, and for the two regression coefficients would be 0.5. And if there were no missing data, since I have a simple random sample, there are no issues. I would get unbiased estimates, of course. My variance estimates work pretty well, so my estimated variance over the true variance is always close to 1. So I have an unbiased variance estimate. And my coverage rates, of course, are also close to the nominal coverage rate of 95%. Okay, so everything works fine here. Now, what happens if I do complete case analysis? So basically, I'm throwing away all the information that I have in Y2 and only use those cases where Y1 and Y2 are observed. Now, for missing completely at random, everything would still work fine. Everything would still be unbiased. My coverage rates are okay. So in this situation, I would still be fine. But as soon as I get to missing at random, things start to get problematic. So my mu would be biased, the mu for Y1, and my first regression coefficient would also be biased. I'm only getting unbiased results for the regression coefficient of Y2 and the regression of Y1 on Y2 under missing at random, and I get unbiased results under missing not at random for the regression of Y2 on Y1. Okay, so these are specific situations. You can show that if the missingness does not depend on the dependent variable, you can still get unbiased results using complete case analysis. Okay, but in all other cases, you'll get biased results. Okay, so this would be, again, another misconception. People think as soon as we are in missing not at random situation, everything will always be biased. It's not necessarily true. So if you run a regression model and you have missingness only in the explanatory variables, and the missingness depends only on those explanatory variables, you still get unbiased results. Okay? Important here, the important message is just that for 5 of my estimates, I still get unbiased results and the correct coverage rate. Okay, just keep that in mind when we look at the results for the different imputation methods. The first one is a very simple one, unconditional mean imputation, where you simply put in the mean of Y1, the mean of Y1 ops, so the observed mean from your data for all those cases where Y1 is missing. And obviously, if you do that, you'll underestimate the sample variance once you filled in the data, because the variance of the imputed values is 0, right? They all get the same value. And similar problems will arise with covariances, or if you look at percentiles of your distribution afterwards, or measures of shape, which is pretty obvious. And this method would be classified as deterministic. We don't have any error term. It's univariate because we don't condition on any other variables. And generally, the relationship with the other variables would be distorted. But regarding my imputation model that we looked at, it would just be like regressing only on the intercept, right? So this would be my imputation model. And this is what it would look like. I mean, these are my observed, the black dots are my observed cases, the red dots are my imputed cases. And I mean, it's pretty obvious that this is not a very useful imputation method because it clearly distorts the relationship between Y1 and Y2. And if you look at our results again, we can see that even under missing completely at random, we get biased results now for some of the coefficients, right? And under missing at random, everything is biased. Under missing not at random, we only have that one coefficient that is still unbiased. Okay, but if we look at the variance ratios, so again, this is the average estimated variance over the true variance, we can see this is always biased. Our variance estimates will always be wrong. We have some situations where it's not too bad, and in those situations we are just slightly conservative with our coverage rates, but in all other cases we are really far off. Right? So now if we look at that, we see that only 2 estimates are somewhat acceptable and everything else is really, really far off. So before you do that, you better stick with your complete case analysis, right? It's not a good idea to do mean imputation for sure. One other example that is often used, and I don't have that included in my simulation because it's for longitudinal data, but I still want to discuss that briefly, is last observation carried forward, which is especially popular in medical studies and clinical trials, because you're often confronted with a problem that you have dropout. I mean, we also have that with all longitudinal surveys. People are bored, they don't want to participate anymore, so we have dropout. And last observation carried forward simply means that you simply carry the last value that you observed from the last time the unit participated. You simply plug that in for all future time points. Okay, so in some sense it's also like it's a deterministic imputation. And of course it's a very simple strategy, which often is the main reason why these imputation methods are used. They are simple, but it's based on the very strong assumption that the value of the outcome remains unchanged after dropout. And of course, you can easily imagine that this is very unrealistic. So if you think of those clinical trials, those units that drop out, so if you consider, say, those in the control group, they might drop out because their conditions get worse and worse, and the doctor decides we cannot leave that person in that control group. They really need to get treatment, right? So, and obviously their condition would decline even further if you would not give them any treatment. So it's totally unrealistic to assume it would remain constant. And similar with those in the treatment group, you could say maybe the side effects for those units were so strong that they got worse health condition and they needed to leave that study. So obviously this is not a realistic assumption and causes a lot of trouble and bias in your data. So again, not a good idea. But coming back to the cross-sectional imputation methods, the next step from unconditional mean imputation would be conditional mean imputation. So where you set up a set of adjustment cells, so other variables that you use, you might cross-classify a set of fully observed variables, and then you impute the mean within those adjustment cells. So you compute the mean of the observed cases again within the adjustment cell and just impute that. Okay? This is basically similar to weighting by the inverse of the proportion of respondents in each class. Not really clear what you do with categorical variables there, but can at least use it for continuous variables. It's deterministic. It's multivariate now because we're conditioning on other variables. And my imputation model now is a little bit more complex in the sense that now I have some predictor variables here, but all these predictor variables would be categorical. Okay? And what would my imputation look like if I do that for my data? So what I did here is, oh no. What I did was I simply used Y2 and used 10 quantiles. I used the deciles of Y2 and then always imputed the mean of Y1 within those deciles of Y2. Okay, and then you get this staircase imputation picture, of course, because Y1 and Y2 in my situation are positively correlated. So the average y1 value will always increase with each subclass. But of course, still we do not reflect the true relationship between y1 and y2. And this is also reflected if we look at the results for this simulation again. We can see now that at least, so the mean is more or less unbiased with missing completely at random and missing at random. And also the regression coefficient of beta 2 is at least getting close to the 0.5 again. It's not strictly 0.5, but we are getting there. And if I would have defined finer quantiles for y2, I would get closer and closer. But we still have that same problem that we totally underestimate the variance of those point estimates. So my coverage rates now are way too low for all the estimates. So again, I would be better off using complete case analysis here. Okay. So next step, now we do regression imputation. So instead of defining these adjustment cells, I use my predictor variables, and these could be any predictor variables. These could be continuous or categorical or predictor variables. I just run a simple regression model and impute those missing values by getting the estimates of this regression model based on the original data and then predicting the missing values just by using those estimated beta 0 and beta j. Okay, this method is still deterministic because we still have no error term, but it's multivariate because we condition on those C variables. And if C would only contain categorical variables, we would basically be back at the, which would be similar to the imputing means within adjustment cells. Okay. Now, what would that look like? I mean, we're getting closer in the sense that at least we're now modeling the relationship between y1 and y2, but you can still see that clearly we are not reflecting the variability of y1 properly, right? And so if we look at the results again, we can see now that finally the mean and the regression coefficient beta 2, they would both be unbiased under missing completely at random and at random, but beta 1 would still be biased. Okay, and this is again, I think, one example where I would say a common misconception that you think if I use regression coefficient, regression imputation, I might underestimate the variance. I mean, this is obvious since I'm only predicting values right on the regression line, but at least my point estimates should be unbiased. But again, this is not the case. So you can see that for beta 1 here, in missing completely at random and missing at random, in both cases it will be biased. Okay, so even the point estimates are biased. So still, not better than using complete case analysis. So what are the general disadvantages of conditional mean imputation? It is true that under missing at random or missing completely at random, this conditional mean imputation provides the best point estimates of the missing values in the sense that they would minimize the expected square error. So again, it would be the optimal prediction in a way. But as we discussed already, prediction should not be the only goal when we think about imputation. I mean, prediction is good. Of course, we want to get into this to the right ballpark, but we still need to account for the uncertainty because otherwise we will totally underestimate the variance, okay? Which then would mean that especially the associations are generally distorted. And of course, this is especially problematic if you're interested in the standard errors. So if you want to do testing or other stuff, or if we're interested in the tails of the distributions, because we generally underestimate the variance. Okay, so as a consequence, my p-values will be too small. I would declare coefficients to be significant, even though they are not. All these things, and generally, my inferences will be invalid. So we take the next step. So instead of using deterministic imputation, we do stochastic imputation now. Okay, so instead of filling in the conditional means, we use random draws from the predictive distribution of the plausible values and not from the center of the distribution. So now we finally have a stochastic imputation method. It's stochastic and it's multivariate if we use the regression model. So now we have the regression model again, but we have that error term in addition. Okay, so and this error term is simply a random draw from a normal distribution with expectation 0 and a variance that's equal to the residual variance that I got when I fitted my regression model to the observed data. Okay? Now we have stochastic imputation. And if I look at that, that looks pretty good in the sense that my imputed values basically follow the same pattern as my observed values in that example. Okay, so we can see that now we are preserving the distribution and the relationships between y1 and y2 in our imputed data. Okay, and if we look at our simulation results, we can see that finally it's the first time we are better than complete case analysis in the sense that our point estimates are unbiased for all cases as long as we have missing completely at random or missing at random. So everything is unbiased here, which is great. And the missing not at random, we lose the nice effect that we had with complete case analysis that beta 1 was unbiased. We don't have that anymore. But at least we have unbiased results for all estimates on the missing completely at random and missing at random. But one major problem still remains, and this is the variance ratio. So my estimated variances are still way too small compared to the true variance of my estimates. And as a result, my coverage rates are still quite low. Okay, so I can get unbiased point estimates, but in terms of inferences, I still get biased results. So as a summary in general for imputation methods, I think this is the main problem, that these simple imputation methods are still often used in practice, especially things like mean imputation. And people don't think enough about the consequences, the bias that is introduced by using these simple methods, and that in many cases you might actually be better off not to do anything at all before you use these simplified methods. And of course all deterministic models will underestimate the variance, but the major problem is that even stochastic models will underestimate the variance because we don't reflect the uncertainty that comes from our imputation. Okay? But the real problem is those imputations are not real values, right? It's only a guess about those missing values. And since it's only a guess, we need to account for the uncertainty that comes from that guess, right? And how should the software know that you're only guessing for some of those cases that you have in your data? Your software doesn't know that, and so cannot account for that. Okay, but again, we only want to obtain valid inferences based on the observed data and not recover the missing values. And so the best thing we can do is to estimate the distribution of the missing data given the observed data under the specific assumptions that we make about the missingness mechanism. Okay, and this is what I already said. We only have those guesses. These guesses lead to additional uncertainty, and we need to make sure that we somehow account for that uncertainty when we analyze the data. So some general recommendations regarding imputation methods. First of all, imputations should always condition on observed variables. First, to reduce bias due to non-response. So as soon as we are not in the missing completely at random situation, we can reduce bias if we condition on other variables, on the observed variables. We can also improve precision, right? Because if my variables I'm conditioning on are good predictors of my variable I'm imputing, I will always improve the precision of my imputations. And of course, I also need to do that just to preserve the association between the missing and the observed variables. So just the example that I gave with income and education. We need to include education as a predictor to ensure that the relationship between income and education is preserved in the imputed data. Imputation should also be multivariate to preserve association between the missing variables, and this is a little more tricky because in practice, of course, it's not the case that I only have missings in one variable and everything else is fully observed, like we had in that simple simulation design. In practice, of course, you have missings all over the place, and then preserving the relationships between all those variables with missing data is a little more tricky, and I'll talk more about that tomorrow. And finally, it's important that imputation should be draws from the predictive distribution rather than means, again, to provide valid estimates of a wide range of estimates. So again, not only to account for the uncertainty, but to really ensure that all your estimates will be unbiased. But the major problem that we have with all methods that we discussed so far is that they still don't account for the imputation uncertainty, and so we'll always underestimate the standard errors, and the consequences are that the p-values that we compute from our imputed data will always be too small, and confidence intervals that we compute will be too narrow, right? So if I do testing, I will declare certain coefficients to be significant too often, okay? And there are various ways how we can take this additional uncertainty into account, and Tan mentioned that already this morning. What you could do in some specific situations is actually to adjust your variance formula. So for specific types of estimates and specific imputation methods, you could actually derive what the correct variance estimate would be in this situation if you use that imputation method. The only downside is that this only works for a very limited number of estimates. So you can derive that for the mean of your imputed variable in some situations. But as soon as you want to look at more complicated regression models, it's typically not possible to derive explicit formulas for the variance. Another strategy could be that you modify your imputations in such a way that the standard errors will be correct, computed from a single filled-in data set. So in some sense, you inflate the variance during the imputation. So you increase the variance in the error term that you use in some sense, so that once you analyze the data, you get unbiased results, but it's the same problem. This would only work in very specific situations for very specific estimates, so it's very limited. The only general approaches that you have would be either, as Tan said, use these resampling methods. So you could use Bootstrap or Jackknife. The only problem there is that what that means is that you would have to do the imputation for each Bootstrap or Jackknife replicate, right? So it's not that you can impute the data once and then use your Bootstrap on the imputed data, but you would have to take Bootstrap samples from your observed data and then impute the data within each Bootstrap sample and then estimate the variance from that. And I mean, you can do that, but of course, if you think that with Bootstrap you would need 1,000 replicates or something, that also means you need to impute your data 1,000 times. So I think these days with the computational power, it's actually an option. It's not that I would say this is generally not an option, but you need to consider the computational demand of that approach. And then finally, we have multiple imputation as an alternative way to account or be able to estimate this additional uncertainty that comes from imputation. And of course, this will be the topic for tomorrow morning then, and then I'm finished. Thank you.
Questions? Yes. ¿Habrá alguna pregunta que quisieran hacerle al profesor Dreschsler?
Hello. So what would be the best amputation method for clinical trials?
So imputation in longitudinal context is of course a pain. Imputation generally can be a pain because specifying good imputation models is a lot of work, and you can spend a lot of time on that. I would say approaches that would work would be based on mixed effects models, multi-level models, where you try to account for the hierarchical design of your data, because you have observations clustered within individuals. And so that would be my general direction to go for. But of course, depending on how many variables you have, it might be difficult to fit those models. But at least I would think in that direction, using mixed effects models for that.
¿Alguna más? Bueno, creo que ya todos queremos pasar acá. Eric.
En español podría ser. Could I speak in Spanish?
No, I'm not sorry. I need to. Thanks.
¿Cómo podríamos identificar si los datos que tenemos pertenecen a perdidos de manera aleatoria, perdidos totalmente aleatoriamente o perdidos no aleatoriamente? ¿Cuál es la forma de saber mis datos perdidos a qué grupo pertenecen?
Okay, this is the general problem you're facing. I mean, there is a way that you can distinguish between missing at random and missing completely at random. Just, I mean, very simply, you could create an indicator whether the variable is missing or not, and then regress it on your other variables. And as soon as some of those variables turn out to have a significant influence on that indicator, you already know you're not in the missing completely at random situation. But again, there's no way that the data will ever tell you whether you have missing at random or missing not at random. It's just not, you cannot learn that from the data. There's no way to use your data to get that information, because just if you're in the missing not at random situation, the problem is those parts of the data that would tell you are missing, right? So you simply, unfortunately, cannot get that information from your data.
Thank you.
Bueno, pues agradezcamos al profesor Dreschsler por su presentación. Thank you for your presentation. Y creo que ya es tiempo para el lunch.